Back on December 5th of 2016, Klay Thompson had a legendary game where he scored a total of 60 points in only 29 minutes played. Let's take a look.
Klay Thompson drives in for a layup. Then Klay Thompson, another three. And we'll just tell you, Klay had a cool career high 60 points in just 29 minutes of action. The Raiders QB Derek Carr in the house, loving every minute of it because Golden State gets the big W. Your final score 142 to 106.
Klay, career high, 60 points. Oracle Arena chanted your name. What was it like hearing that?
Well, it felt great, obviously.
Now, Klay's sequence of shots provides a very useful data set for exploring the question, is there a hot hand phenomenon in the game of basketball? Do players experience hot streaks and cold streaks in their shooting? Does knowing the outcomes of past shots help us to predict the outcomes of future shots? So let's look at the sequence of Klay's shots. There were 44 shots in total. Let's go ahead and encode the sequence with a 1 when Klay made the shot and a 0 when Klay misses the shot. And the sequence does look a little bit streaky. We do see instances where a whole bunch of 1s appear all in a row. There's plenty of instances where there's 4 1s in a row. And there's even one instance where 6 1s appear all in a row. And that does look a little bit streaky. So maybe this is evidence for a hot hand. We'd like to learn from a statistical point of view, how do we go about really testing this? There's a whole world of hypothesis testing in the statistical realm, and we'd like to learn how to pull that off. If we have some sort of question about the world, like is the hot hand real, how do we use data to explore that question? Now, among basketball players and basketball fans, the idea is that the hot hand is very real. In fact, psychologists from Stanford and Cornell did a survey where they collected a bunch of fans of basketball, fans that had played basketball at least occasionally, and that had watched at least 5 games per year, and they asked them a few questions about the existence of a hot hand. So they asked, is it important to pass the ball to someone who has just made several, maybe 2, 3, or 4 shots in a row? And 84% of those fans said yes. They asked another question. Does a player have a better chance of making a shot after having just made his last 2 or 3 shots than if he had just missed the last 2 or 3 shots? And an overwhelming 91% of fans agreed that he had a better chance of making the next shot if he had just made those last few. And among basketball players themselves, these percentages are even higher. Now, this isn't a new question to really study. People have studied the existence of a hot hand for really quite a while. The original research paper back in the 1980s, which concluded that there was no hot hand, turned out to have some pretty deep statistical flaws, and people have had to improve on the research since then. And there's really no shortage of YouTube videos, articles, and even academic research looking into the question on whether or not this hot hand phenomenon is real. And at the latest, it looks like that there's a little bit of evidence for a hot hand, but it's definitely not something that is an overwhelming effect in the sequence of basketball players' shots. Now, if you're a basketball fan or a basketball player, you might vehemently disagree with that statement that if there is a hot hand, the effect is actually relatively weak. So let's learn how we can study this, answer this question, or study this question from a statistical point of view. So when we look at Klay Thompson's sequence of shots, fundamentally we have the question, is this sequence consistent with an ordering of 1s and 0s that can happen just by pure chance, a purely random arrangement here, or is the streakiness that we think we're seeing really evidence of a hot hand? So I guess the first thing that we need to do is figure out, well, just how streaky is this sequence? What can we measure from the data that helps quantify how streaky that sequence really is? And in statistics, we very often do this by measuring the number of runs in a sequence. Now, a run is going to be a sequence of all 0s in a row or all 1s in a row. So if we look at Klay's sequence, we find that it starts off with a run of 1s. We have 2 1s in a row. We have a run of 0s, really only just 1 0. And then we have a pretty long run of 1s. We have 4 1s in a row. So what we could do is we could count up the total number of runs and maybe use that as a measure of how streaky that sequence is. You know, if we measured a very small number of runs, that's evidence that the sequence is very streaky. You know, a whole bunch of 0s followed by a whole bunch of 1s, etc. If instead we had a very large number of runs, well, that means the sequence must alternate from 0 to 1 and back and forth really quite frequently. So that's something that we can measure from the data. The numerical value of the number of runs is somewhat sensitive to how streaky that sequence is. And so we just have to ask ourselves, okay, well, what do we expect for the number of runs for a truly random sequence here? If we were to arrange these zeros and ones at random, do we expect to see 10 runs, 15 runs, just 2 runs? What can we expect to see from purely random sequences? And so we have Klay Thompson's sequence, but how can we generate a sequence at random here? Well, we're used to generating random numbers with the sample command or the R version of our notorious distributions. But if we think about it, actually generating a random sequence of baskets that are made or missed is a little bit more complex than what we're used to. It's not like we can just use the sample command, drawing from the vectors 0 and 1, say with replacement, because we don't actually know what the probability of observing a 1 is, and we don't know the probability of observing a 0. We don't know the probability that Klay is going to make a shot or actually miss a shot. Sure, we could estimate that relatively poorly from this relatively small data set, but what if that probability changes over time, or maybe from game to game? So we need some way of really coming up with a method to glimpse at how the sequence might have turned out if it was being generated purely at random. And there's a clever way to actually go and do this, and that is to permute the values that have been observed. Now, by permuting, all that means is taking the observed 1s and 0s and just randomly rearranging them. That way, if we randomly rearrange those 1s and 0s, we're guaranteed to end up with a purely random sequence. And the nice thing is that we've kind of skirted the question of, well, what is the probability that Klay actually makes a shot? That doesn't factor into it. In fact, we don't know. We don't really need to know in order to help answer our question. Fundamentally, the question was, okay, is Klay's sequence, a representative example of a purely random sequence, or is something fishy going on? Is there a hot hand going on here? So if we just randomly rearrange the 0s and the 1s, that provides us a sequence that's generated purely at random, and we can compare Klay's sequence to the properties of purely random sequences. So how do we do this? Well, in R, there's actually some really nice commands that allow you to extract out the number of runs in a sequence, the run lengths. Do we see a run of length 7 1s in a row, or 7 0s in a row? That allows us to, after we permute the originally observed 0s and 1s, to actually measure quite efficiently the total number of runs or any of the run length properties that we have in mind. So let's go ahead and do this for Klay's sequence. Let's randomly rearrange those 0s and 1s, the shots that he made, the shots that he missed, and count up the number of runs that result in these now purely random sequences. Now, when we do this, we actually see a pretty large variety for the total number of runs, anywhere from less than 10 up to more than 25 or so. So there actually is a pretty big variety in the number of runs that we expect to see in a purely random sequence. And if we go and count up the number of runs that we saw in Klay's sequence, it turns out that Klay's number of runs is actually kind of on the larger side when compared to the number of runs for purely random sequences. And this is actually evidence of not being a hot hand, because it's only small values of the number of runs that provide evidence of a hot hand. Small number of runs means that it's very streaky, long sequences of 1s followed by long sequences of 0s, etc. The larger the number of runs, the more it's often it's switching from 0 to 1 here, the less evidence we would have for a hot hand. So, in fact, Klay's number of runs is a little bit on the longer side compared to what we would expect just from a random sequence, definitely not evidence whatsoever of some sort of hot hand. But there are other ways of measuring streakiness of a sequence of 0s and 1s, and I think this next definition really hits home and really captures what it means to have a hot hand. So let's examine just those shots that Klay Thompson made. Well, what fraction of the shots that happened next did he also make? If he's in the zone, if he's experiencing a hot hand, well, if he just made a shot, the chance that he'll make the next shot should actually be fairly high. So what if we measured that from the data instead? What if we looked at the fraction of shots that were made that were immediately followed by another shot that was made? Well, if we go and we measure this, we have to be a little bit clever in the way that we code this into R. But with a little bit of programming, we can figure out how to measure this from just some arbitrary sequence of zeros and ones. And we can do the exact same thing. We can measure the value from Klay's sequence. We get a value of 0.63. 63% of the shots that he made were immediately followed by another shot that was made. And we can see how this number compares to a purely random sequence just by permuting the ordering of the zeros and ones in the data that we've collected. Now, when we do this, we see actually quite a large variety in this fraction, anywhere from about 55% up to around 85%. And we just have to think about, okay, well, what values would be evidence of a hot hand? Well, evidence of a hot hand means that if you just made your shot, you're probably going to make that next shot. So large values of this fraction would be evidence of a hot hand. And when we look at the properties of purely random sequences, we actually see that Klay's number here, the 63%, is really quite ordinary. In fact, a large fraction of the time, a purely random sequence has a higher percentage of shots made that are immediately followed by yet another shot that's made. So, in fact, from this point of view, it doesn't look like Klay's sequence is any out of the ordinary from what we would expect from purely random sequence. This is definitely not good evidence of a hot hand here. And so even though that original sequence might have looked a bit streaky to our eyes, it turns out that, our mind isn't the best at really fundamentally understanding what randomness looks like, what a random sequence looks like. It's pretty easy for us to get fooled into thinking there's a pattern when there's not, because our brains are developed for pattern recognition. And it turns out that looking at Klay's sequence of shots really just leaves us with the big old shrug. It's like, yeah, that looks actually pretty consistent with what we would expect at random, just the random ordering of zeros and ones. Definitely nothing to write home about in terms of evidence of a hot hand. Now, these sorts of questions actually arise quite a bit in analytics. If we are looking, let's say, at the movement of stocks up and down, and we want to come up with the new best investment system, we might like to know, well, can we predict the future movement of stocks? Yes or no? So if we can predict movements up and down, we can make some pretty wise investments and probably make a lot of money. So we'd like to know the answer to that question. Can we predict the movement of stocks here? If we're working for a company like Hanes or some other clothing company, we might like to know if there's any difference in the return rates of the different colors that we sell a particular product. If there is, I want to identify, well, which product has the highest return rate and maybe take some action about that to maybe reduce the return rate there. Or maybe you're working in traffic engineering. Your job is to make sure the light timings are optimal, and so you need to know if traffic patterns have changed since the last time you set up those timings. So yes or no, does traffic look like it's a little bit different and therefore require a different set of timings? If you're working in advertising or marketing, you might have two different designs of ads that you've come up with, and you would like to know, all right, well, do these have the same click-through rate or is there one better? And so there's a huge field of statistics that deals with answering these sorts of questions, yes or no questions here. And this field is called hypothesis testing. Now, this played a huge role, I would say, a couple of decades ago. I would say that especially in analytics, the world of hypothesis testing is kind of a niche world in this point. There are a few questions that we have to answer inside the hypothesis testing framework, but in business analytics, most of these questions are going to be better answered with confidence intervals. Because if we want to sit down and ask the question, okay, well, is there a hot hand in basketball? We immediately want to follow that up with, well, how big of an effect are we talking about? Just how streaky are these sequences? Hypothesis test might let us know yes or no if there's a hot hand or not, but we immediately want to know, well, how streaky are we talking about? How big of an effect? If we're looking at the difference in return rates across many different products, hypothesis test might tell us that, yep, they're not all the same, but we immediately want to follow that up with, well, just how big of a difference are we talking about? If two ads have a difference in click-through rates, we want to know if it's big enough for us to really care, or if, it looks like one ad, for all intents and purposes, are basically equivalent to one another. So in the world of business analytics, where we're all about actionable insight, the hypothesis test typically leaves us hanging because we have additional follow-up questions like how big of a difference are we really talking about? How much has the traffic patterns actually changed? If we have some sort of question about theta, some parameter like a probability, an average, a parameter of a probability distribution. If we want to know, is it this value, we make our 95% confidence interval to get a range of plausible values for theta, and we check to see if our value of interest falls somewhere inside. If it does, well, we would say, sure, looks like it's plausible that theta is equal to that value of interest. If that value is outside the confidence interval, we say that, no, it's really not that plausible. It's not really consistent with the data that we've collected. We haven't outright eliminated it from possibility. We could always have a quirky sample, but it definitely is not consistent with the data that we've collected. So, upshot is, if you have a question about the probability of some event, the average of some probability distribution, or the parameter of some probability distribution, make a 95% confidence interval and use that to answer your question. A hypothesis test really comes back with a yes versus no, and as business analytics practitioners, we're always yearning for a little bit more. Now, unfortunately, we just can't use confidence intervals for everything. We do need that formal hypothesis testing framework to help answer a few questions. If we had some sort of an idea about what probability distribution was generating the data values that we're collecting, maybe we think that the items in a cart at checkout is well described by a zero truncated Poisson distribution, it's not like we have a confidence interval for what distribution is making that data. And with the hot hand example, it's not like we have a confidence interval for the streakiness of a series, how much of a hot hand it really is. And this is these cases where we really need the hypothesis testing framework. So let's talk about this. How do we do a formal hypothesis test? If we need a yes or no answer out, how do we do this? So when we set up a hypothesis test, we really sit down and ask ourselves three things. Number one, really, what is the question that we're asking? Number two, what are we going to measure from the data to help us answer that question? And number three, how exactly are we going to come up with a conclusion? And so let's go through some of these steps one by one. And really the most important thing is making sure that what we're asking the right question when we're setting up our hypothesis test. So step one is actually setting up the hypotheses. And since a lot of good things come in pairs, well, there's actually two hypotheses that you're going to set up in any hypothesis test. One is going to be called the null hypothesis. We'll abbreviate that by H0. And the null hypothesis is going to say something very specific about the probability distribution that's generating the data that we've collected. So it might be about an exact value of p. Is p equal to 50%? It might be about the difference in averages between two different groups. Is the average 0? Or it might be just about the probability distribution itself. Is the probability distribution a zero truncated Poisson? With the hot hand example, maybe the null hypothesis would be that the sequence is just random. There's no hot hand here. Now the alternative hypothesis, we're going to abbreviate with an HA, A for alternative. And in general, the alternative hypothesis is going to contain our claim of interest. It's going to be some sort of statement about that probability distribution that requires extraordinary evidence to believe. So maybe we think that the probability of some event is bigger than 60%. We need to have evidence to establish that. We want to establish the presence of a hot hand. That takes a lot of evidence to establish. That sort of claim would go in the alternative. If we think that one design of an ad is better than the other, well, we need evidence to really believe that. That's going to be the claim that goes in the alternative hypothesis. And so the way that a hypothesis test proceeds is that we're going to start out by overwhelmingly favoring the null hypothesis. We're going to start out favoring the null hypothesis, and we're going to continue to do so until the evidence suggests otherwise. And we're going to have a lot of evidence to favor the alternative hypothesis. So here's one way that you can think of a hypothesis test. Let's imagine that you are up a little bit later than you usually stay up at night, and you hear a loud crash from somewhere inside your house. So you immediately take note and you start wondering, uh-oh, what's going on here? Is someone trying to break in? Did the house just settle? Did something fall over downstairs? And so when you go into this investigation, your null hypothesis is really that everything is okay. It's not like you're calling up 911 and the police every time you hear a strange sound that you can't quite explain. Your null hypothesis, the claim that you're going to continue to favor until the extraordinary evidence suggests otherwise, is that everything is okay. So you get up from where you're sitting, you go and investigate, you check some of the windows, you check some of the doors, you look to see if anything's fallen over. And unless the evidence suggests that something fishy is going on, like you have a broken window or a window that's open or a door that's open, then you're going to continue favoring the null hypothesis that everything is just okay. In order for you to favor the claim made by the alternative that everything is not okay, that someone's trying to break into your house, you really need to have that evidence that says, uh-oh, something is really going on here. You got some broken glass. You got the door that is suddenly ajar here. So another way to think about how a hypothesis test really proceeds. So some examples, let's imagine that you're interested in hiring some sort of marketing firm, and this marketing firm claims that its ads have a click-through rate of 1 out of 40. And you're a little bit suspicious because that looks a little bit high, and you believe that they're overstating their success. And so to call them out, you're going to collect some data, and you're going to run a hypothesis test about P, the probability that someone's going to click on that ad. So what's going to be the null? What's going to be the alternative hypothesis? Well, the null hypothesis is going to say something very specific about the probability distribution. In this case, we're going to set it up so that the null is that the probability of clicking on an ad is exactly equal to 1 out of 40. The alternative is going to have our claim of interest. We're a little bit suspicious about that claim. We think it's a little bit less than 1 out of 40. So in the alternative, we're going to say that P is less than 1 out of 40 here. And the way the test will proceed is we'll say, okay, we'll give the marketing firm the benefit of the doubt. We'll maybe show a bunch of ads to a bunch of different users, and we'll just see how that click-through rate measures up. If it's substantially below 1 out of 40, well, maybe that's going to be enough evidence to favor the alternative hypothesis. We'll start out kind of believing the marketing firm, saying, sure, we'll favor your claim here, but if the evidence suggests otherwise, we're going to favor the alternative. If we're asking our question about, is there a hot hand in basketball? What's going to be the null? What's going to be the alternative hypothesis? Well, in that alternative is get our claim of interest. It's what we are going to have to establish through overwhelming evidence. So in the alternative, there's a hot hand. The null is going to be the opposite here. The null is going to be like, nope, no hot hand at all. The sequence is purely at random. So one last example, we might be interested in looking at whether or not there is or isn't clustering in lead poisoning cases in a city. Are the cases distributed purely at random, or are there, clusters of cases that are, suspiciously close to one another? So what would we put for the null? What would we put for the alternative hypothesis? Well, our claim of interest is really that there's some sort of clustering. That would give us information that we can act on. And so our claim of interest finds itself in the alternative hypothesis. The null hypothesis is going to be the opposite, basically that there's no clustering going on. It's a purely random assortment of points that we're seeing in front of us. And there's actually a good reason why that's the null in the alternative. Remember, the null hypothesis has to say something very specific about the probability distribution that's making the data. Once we say that the assortment of points is randomly distributed, that fully specifies the probability distribution. It's a uniformed kind of collection of points in this square. Clustering is kind of an ambiguous process. There's a lot of different ways you could cluster points. And so saying that the points are clustered isn't really specific enough to fully specify that probability distribution making these locations. And so that's another reason why the null and the alternative are set up the way that they are. So when we set up our null and our alternative hypothesis, we have a very specific way of writing this down. Our abbreviations are H0 for the null hypothesis, HA for the alternative hypothesis, and if there is any sort of lingering doubt about which one goes in the null, which one goes in the alternative, it's pretty easy to remember the null hypothesis is always going to contain some sort of equal sign. So once we've established that, we need to really sit down and ask, okay, well, what really is the question that we're trying to answer here? And there are three different ways, three different questions that the hypothesis test framework is really used a lot in statistics. One might be a two-sided test, where our null hypothesis is that theta, this parameter that we find interesting, is exactly equal to a particular value. So are we dealing with a fair coin? Is p equal to 50%? If we're dealing with a two-sided test, that means that we don't really care if the true value of p is bigger than that number or smaller than that number. We just care that it's different than the value that we've specified in the null hypothesis. So the two-sided test is going to have as the alternative hypothesis that theta is just not equal to that proposed value. We don't care if it's bigger or smaller. We just care if it's different than that proposed value of theta. Now, we do have one-sided versions of hypothesis tests where we really only find interesting or really only care about one side of the true value of theta. Is it bigger than the proposed value that appears in the null, or is it smaller than the proposed value that appears in the null? With that marketing firm example, we were really curious to know, well, is the click-through rate less than the 1 out of 40 that the marketing firm was claiming? So in some sense, the only values of theta that we find interesting would be values that would be less than that 1 out of 40. Now, the vast majority of time when we're talking about one-sided versus two-sided hypothesis tests, our questions are going to be about probabilities and averages. And in that case, we really want to be using confidence intervals to answer these questions. So let's discuss how we use confidence intervals to do the two-sided tests and the one-sided tests. And so let's tackle the two-sided test first, because we've already discussed this in the context of estimating probabilities and averages. So in the two-sided test, we have a very particular value of theta in mind. Our null hypothesis is that theta is equal to this value. The alternative is that it's somehow different. So take, for example, your midterm scores. It might be the case that I want to curve the scores on the midterm so that the average is, say, an 84. Now, if I were to go and look to see what the average was on the midterm scores from your class, I might find a value that's right at about 80 or so. And so I would like to know, okay, well, is 84 a plausible value for the true average of whatever probability distribution's making this data? Or does it look like it's a bit different? Essentially, I want to run the hypothesis test. Is mu equal to 84, or is mu different than 84? And we know how to make the confidence interval. We shoot that into t.test, and it turns out that we're 95% confident that mu is between 76.9 and 82.97. So 84 is not inside that confidence interval, and so we say that 84 is not a plausible value for the average based on the data that we've collected. So it looks like I need to do some curving. If I really wanted 84 to be the average, it doesn't look like, based on the scores from this class, that the average is 84, so I need to make some sort of adjustment. On the other hand, let's imagine that I may be interested in curving homework scores. Let's say I want the average to be 82. Well, if I go and look at the data and shoot that into t.test, I find the averages are right about 80, a 95% confidence interval for the average of whatever probability distribution's making these numbers. It goes from 77.5 up to 82.55, and it looks like that since 82 is right inside that confidence interval, I wouldn't need to do any sort of curve. 82 is a plausible value for the average of that probability distribution based on the homework scores that have been collected. So when we have this two-sided test, is theta equal to this particular value? Is it different? Go ahead and make your 95% confidence interval the standard way with binom.test, prop.test, t.test, whatever test in R, and look to see if that value of interest is inside that confidence interval. If it is, well, we continue to favor the null hypothesis. If it isn't, we're going to favor the alternative hypothesis. That's enough evidence for us to favor the alternative instead of the null. So what about these one-sided tests, where only certain values of theta are interesting to us? So, for example, maybe we only want to change our investment strategy if the probability of doubling our money over the course of 5 years with the new investment strategy is larger than 60%. Maybe our current investment strategy, that probability is 60%. We're only going to change if the new investment strategy has a probability that's bigger than 60%. So we write up a Monte Carlo simulation, maybe to simulate the markets. We run it a total of 100 times, and we find that in 70 of those 100 times, we do end up doubling our money over the course of 5 years. So our best guess for this probability is 70%. That's definitely bigger than my 60% threshold, but is it large enough for me to really favor that the true probability is bigger than 60%? Or is measuring a value of p hat 70% perfectly consistent with just kind of random chance here? So how would we conduct the hypothesis test where p is equal to 0.6 versus p being greater than 0.6, our claim of interest, with a confidence interval? Well, in this case, we're going to make a small tweak in our confidence interval because what we're really interested in figuring out is what is the smallest possible value of p that's consistent with the data that we've collected. So a one-sided confidence interval in this case is going to look like some lower bound all the way up to positive infinity. So how do we actually do this? Well, we're still going to use binom.test, prop.test, t.test. We're just going to add in the additional argument, alternative equals, and then greater in quotes. So how can we remember what we actually put in that additional argument? Well, if we look at the inequality that appears in that alternative hypothesis, we see a greater than sign because we're only interested in values of p if it's greater than 0.6 in this case. And so that will go and make that one-sided confidence interval for you. We don't really care about values below 60%. That's not going to make us change our strategy. We need to know if it's bigger than 60%. So specifically, we're going to add in that additional argument that lets it know what values we find interesting. So in this case, adjusting the binom.test command to reflect the fact that our alternative hypothesis is that p is greater than 0.6, we get a 95% confidence interval that ranges from 61.6% up to 100%. So that 61.6% is a lower bound on the smallest plausible value of p that's consistent with the data that we've collected. We still run the hypothesis test the same way. We check to see if the value that we've proposed in the null hypothesis, if it's in the confidence interval or if it's not. If it's in that confidence interval, we continue to favor the null hypothesis. If it's not in that confidence interval, well, now that's sufficient evidence for us to favor the alternative. And in this case, I don't find 0.6 anywhere inside that confidence interval, so that's enough evidence for me to favor the alternative. I did measure that 70% of those Monte Carlo simulations resulted in me doubling my money over the course of 5 years. And yeah, it does look like 70% is enough larger than 60% for me to favor the alternative that p is bigger than 60%. So what about the other type of one-sided test? What if the only values of theta that we find interesting are less than the value that's proposed in the null hypothesis? So imagine that we're comparing the return rates of two different colors of products. We have pure orange and we have kind of an orange-red color. And we might want to ask the question, is the average return rate of orange products less than the average return rate of orange-red products here? So what we could do is we could set up t.test, our questions about averages. And in this case, since we're only interested in the case where the average for orange is less than the average for orange-red, we have an alternative that has the inequality that has the less than sign. And that's a little bit of a hint on what we're going to have as our additional argument. So if our alternative hypothesis has that less than symbol, well, we're going to add in that additional argument, alternative equals to less, because what we really want out of this confidence interval is an upper bound on the largest value of that parameter that's consistent with the data that we've collected. So what is the largest plausible difference in return rates between these two different product types? I'm going to be able to use that to gauge whether or not the return rate of orange is less than the return rate than orange-red. So if I shoot this into R, what I find is that I'm 95% confident that the difference in return rates ranges anywhere from minus infinity up to 0.000064. So I have an upper bound for what the true difference is in return rates between those two products. The upper bound is 0.0006. It goes all the way down to minus infinity. Notice that the value inside my null hypothesis would be that the two are equal to each other. 0 appears in that confidence interval, so I continue to favor the null hypothesis here. Not enough evidence that the return rate on average for those orange products is less than the return rate for the orange-red products. So to summarize, if your question is about probabilities, differences in probabilities between groups, averages or differences in averages between groups, use binom.test, prop.test, t.test to come up with the relevant confidence interval. Sit down and ask, well, what's really your question? Are you doing a two-sided test? Are you doing a one-sided test? And adjust the arguments of those commands accordingly so that you get the appropriate two-sided confidence interval or an upper bound or lower bound to help you answer the question. Once you have that confidence interval, it proceeds the same way, regardless of how you set it up. You check to see if the value proposed in the null hypothesis is inside that confidence interval. If it is, you continue to favor the null hypothesis. If it's not, well, that's sufficient evidence for you to favor the alternative hypothesis. So as business analytics practitioners, usually our questions are about probabilities or they're about averages. And so we always want to be using these confidence intervals to help answer our questions because they just give us so much more information than running a hypothesis test. The hypothesis test only tells us which of those two hypotheses we favor, but that really leaves us hanging. If there is a difference in return rates between two products, we want to know just how big they are. If the probability of rolling a 1 on an alleged fair dice is not 1/6, well, just how far away from 1/6 is it? Those questions we can answer with confidence intervals. The hypothesis test framework is somewhat incomplete in that regard. And there's actually a growing opinion among educators and among academics as well. In fact, there are some academic journals that are now forbidding the pure hypothesis testing framework in favor of the researchers making confidence intervals. And I think moving forward, we'll find that hypothesis testing continues to be de-emphasized in education. There are a few questions that we really need it for, but for us as business analytics practitioners, we can really answer most of these questions just with confidence intervals. So if we do find ourselves in a situation where we have to do a hypothesis test, like asking the question, is there a hot hand in basketball? What are the remaining steps that we need to do in order to complete the test and figure out which of these two hypotheses that we favor? So once we've set up those two hypotheses, we need to figure out, well, what are we going to measure from the data to help us figure out which of those two hypotheses that we favor? What can we measure from the data that's going to serve as evidence for the alternative hypothesis? After all, we go into the hypothesis test favoring overwhelmingly the null hypothesis. It's only after a tremendous amount of evidence do we favor the alternative. So what exactly are we going to count as evidence here? Now, in formal terms in the hypothesis testing framework, we refer to this evidence as the test statistic, just the number that we're going to measure from the data whose value is sensitive to whether the null is true or false that allows us to come to our conclusion. So with the hot hand example, we were talking about looking at the number of runs in that sequence, or the fraction of shots that were made that were immediately followed by another shot that was made. Those would be test statistics, something that we can measure from the data that allows us to determine which of those two hypotheses that we're going to favor. And very often you can come up with a choice of different test statistics. They might differ in terms of what we refer to as their power, basically the probability that you'll correctly detect that your null hypothesis is wrong. But you usually can come up with a reasonable choice or two. So for the hot hand example, null hypothesis, there's no hot hand. The zeros and ones in that sequence were placed purely at random. The alternative, the thing that requires a lot of evidence for us to favor, there is some sort of hot hand. We have a choice of test statistics. We could do the number of streaks, the number of runs in that series. Fewer runs is more and more evidence for a hot hand. Or maybe we could look at the longest streak. If we have a sequence of 10 ones, even if all the other zeros and ones are kind of randomly distributed, the fact that there were 10 ones in a row, that's pretty good evidence for a hot hand as well. Or we could use that proportion of shots that were made that were immediately followed by another shot that was made. All three of those test statistics, the values that we measure, are sensitive to whether the null or the alternative is true. So they could be reasonable things that we could use as evidence to help us figure out which of those hypotheses that we favor. If we were asking our question about, are those lead poisoning cases clustered, or are those cases distributed at random? We can't answer that with a confidence interval. We would just need to figure out, okay, well, what are we going to measure from the data to help serve as evidence? What is going to allow us to figure out which of those two hypotheses that we favor? So maybe we could look at the maximum number of cases inside any 2-block radius. The larger the value that is, the more cases that we find in some 2-block radius, the more evidence there is for clustering. Or maybe we look at the largest distance between any case and its 5th nearest neighbor. If that value is relatively small, that means we have at least 5 cases kind of clustered together really closely. Smaller values of that distance would be more and more evidence of clustering. And so once we've determined what we're going to be using as evidence, our test statistic, something that we're measuring from the data, what we need to do is we need to figure out what values of that test statistic would we observe if the null hypothesis were true. Remember, we're going into this hypothesis test greatly favoring the statement that's made by the null hypothesis, so we need to be able to anticipate what values of that test statistic that we might observe when the null hypothesis is true. It's only when we observe something that's greatly out of line with that does that count as sufficient evidence for us to favor the alternative. So we need to get an idea of what we refer to as the sampling distribution of the test statistic under the null hypothesis. Basically, when the null hypothesis is true, what are the values of that test statistic that we're likely to see? So if there is no hot hand, what are the values for the number of streaks or the fraction of shots that are made that are immediately followed by another shot that's made, when these sequences are purely random here? If there is no clustering, what is going to be the largest number of cases we should expect in any 2-block radius? If we're looking at click-through rates, and if the actual click-through rate is 1 out of 40, well, what is, the values of click-through rate that we might measure from a sample when we go and collect data here? We need some sort of handle over what's ordinary, what we might expect under the null hypothesis, for us to know what really constitutes as extraordinary evidence, which is what's required for us to favor that alternative hypothesis. And so once we know what we're measuring from the data that we're collecting, our test statistic, and once we know what values of that test statistic we should expect when the null hypothesis is true, we're basically there to being able to figure out what our conclusion is. If we measure a value of the test statistic from the sample that is very out of line with what we should see when the null hypothesis is true, what we're going to do is we're going to reject the null hypothesis in favor of the claim that's made in the alternative hypothesis. Remember, the way that we do this hypothesis test is that we proceed by favoring the null hypothesis really quite overwhelmingly until the evidence essentially forces us to favor the claim that's made in the alternative. So finding that test statistic that's highly out of line with what we expect when the null hypothesis is true really is what counts as sufficient evidence and forces us to favor the claim that's in the alternative. And so with this in mind, let's go back to the hot hand example to really see where we stand in terms of evidence for or against a hot hand. As our test statistic, the thing that we're going to measure from the data, let's go ahead and measure the fraction of ones, shots made, that are immediately followed by another shot that's made by another one. So if we whip up some R code that says, okay, go and generate a whole bunch of random rearrangements of zeros and ones so that we know what random sequences look like, we can get that sampling distribution under the null of our test statistic. What values of these fractions are we going to observe when we do have just a random placement of zeros and ones? And then we could look to see, okay, well, what are the properties of Klay Thompson sequence? So if we compare purely random sequences to the sequence that Klay Thompson generated that day, we find actually that in terms of this test statistic, there's really nothing extraordinary going on. From purely random sequences, we get values of this test statistic that range anywhere from around 0.55 all the way up to like 83%. Klay's value was 63% here. Really not that high, not high enough to raise any eyebrows, definitely not high enough for us to favor the claim that there is some sort of hot hand going on. So let's formalize the conclusion of our hypothesis test a little bit more carefully. So we've set up our pair of hypotheses. We've figured out what we want to measure from the data, our test statistic. We have a handle over what values of that test statistic we might see when the null hypothesis is true. Formally, the way that we decide which of these two hypotheses that we favor is by looking at the p-value of the test statistic. Now, unfortunately, the p-value is the most misrepresented and misunderstood quantity, I think, in all of statistics. It's a big reason why we're phasing out hypothesis testing from academics, from education. But because it's built into the framework, let's spend some time to talk about what a p-value is and exactly how we use it to determine the outcome of our hypothesis test. So by definition, here's what the p-value is. It's in reference to the test statistic that we measured from our sample. Here we go. So the p-value of our test statistic is the probability, under the null hypothesis, of observing a value of that test statistic that's at least as much evidence for the alternative as the one that you collected in your data. So quick refresher, when we talk about the probability under the null hypothesis, that just means that we're assuming the null hypothesis is true. We got that sampling distribution of what values of the test statistic that we might observe when the null hypothesis is true. It's basically measuring how out of line the value of our test statistic is on the sample that we've collected compared to what we should see or what we expect to see when the null hypothesis is true. And so if this p-value is too small, if it's essentially too unlikely to observe our sample of data values when the null hypothesis is true, then we go and favor the alternative over the null. So what's going to be this threshold for the p-value that's so low that it leads us to favor the alternative hypothesis versus the null hypothesis? Well, this was decided decades ago and we've kind of been stuck with it since, but the threshold is 5%, 0.05. If that p-value is less than 0.05, we reject the null hypothesis and we end up favoring the claim that's made in the alternative. If that p-value is at least 5%, we continue to favor the claim that's made in the null hypothesis. If that p-value is too low, it's letting you know that your set of data values is really highly out of line with what you expect when the null hypothesis is true. And that 5% threshold is just a reasonable threshold that allows us to come up with a nice binary decision. Do we favor the alternative or do we continue to favor the null hypothesis? So in some sense, a p-value helps us to quantify how much doubt we have in the null hypothesis, how plausible that null hypothesis really is. We don't want to overstep the interpretation, though, and actually say that the p-value is the probability that the null hypothesis is true. Remember, in reality, either the null is or isn't true. We just don't know which of these two outcomes it is, and we don't use probability to quantify our ignorance of the world. So the p-value is not the probability the null hypothesis is true or it's false. Rather, it is a comment about the probability of observing your sample of data values that you collected or a sample that provides even more evidence for the alternative had the null hypothesis been the true description of reality here. So just make sure you keep that in mind. The p-value is not a probability about the hypothesis itself. It's about the probability of observing the sample that you've collected. So let's conclude our hot hand hypothesis test with a p-value. So with Klay Thompson's sequence of shots, we found that he made 30 baskets, and in those 30 baskets, 19 were immediately followed by another basket that was made. And so that's what we use as our test statistic, the fraction of shots made that are immediately followed by another shot that's made. Now, Klay's statistic is pretty impressive, but it turns out that that value is something that happened all the time in a random arrangement of zeros and ones. If we go and get the p-value of this test statistic, what fraction of those sequences that were generated purely at random do we find a value of the test statistic that is as streaky or even streakier as the one that we found with Klay's? We find that this happens 96% of the time. And so because this is much bigger than the 5% threshold, what we end up doing is we continue to favor the null hypothesis. We started out favoring it. It required a lot of evidence for us to favor the alternative, and the evidence that we've collected isn't that impressive. We continue to favor the null hypothesis. Now, that 5% threshold that we use for a p-value is really directly related to the 95% confidence in the confidence interval that we can construct to perform that hypothesis test. It's no accident that 5% and the 95% adds up to 100% here. They're basically just two different sides to the same coin, and they come up with equivalent decision rules. Whenever we get that p-value less than 5%, that's going to correspond to the value in the null hypothesis not appearing in our 95% confidence interval. So let's do a few examples where we calculate p-values of some hypothesis tests. We also do it with the confidence interval approach that I think will be helpful. So when it comes to midterm scores, maybe I have the target that the average should be 84. If it's below or if it's above, I need to do a little bit of curving up or down. And so if I take the sample of your midterm scores, what's going to be my conclusion? I'm going to have the two-sided hypothesis test here. The null is that mu is equal to 84. The mu always has the equal sign. The alternative is that mu is different than 84, not equal to 84. Above, below, I don't care. If it's different than 84, I need to do some sort of adjustment. So when I throw in the data values into t.test, I get two things out. I get a 95% confidence interval for the true value of mu. In this case, it ranges from 76.9 up to 82.8. 0.97, I see that 84 is not inside the confidence interval, so it is not a plausible value for the true average based on the data that I've collected. I know I'm going to reject the null hypothesis, and the p-value lets me know that, yep, I end up rejecting that null hypothesis. The confidence interval approach, p-value approach always will give the same thing. So if I look at the p-value of the test, I get a value that's just under 0.1%. So that's less than 0.05, so I know I reject the null hypothesis, and I favor the alternative that the average isn't 84. But let me go ahead and interpret what the value of that p-value really tells us, that p-value of 0.1%. I know that if the true average was 84, there's a possibility that I could collect a kind of quirky set of random data values where the sample average would be 80, like what I observed in this data. The p-value is a comment about how unlikely that really is. So that p-value is the probability, if mu was really equal to 84, that I would observe a sample average like what I collected in my data, or an average that's even more evidence for the alternative, basically a bigger deviation from 84 than the 80 that I observed. Possible, but highly unlikely. That's why we reject that null hypothesis in favor of the alternative. Going back to the investment strategy, where I only wanted to change strategies if the probability of me doubling my money over the course of 5 years was at least, say, 60%, greater than 60% actually. I ran that Monte Carlo simulation. 70 out of those 100 times I did end up having my event of interest occur. And so I can run binom.test to basically answer my question in two ways. I can get that 95% confidence interval, and in this case, what I look for is a lower bound on the probability of doubling my money. A lower bound because it's a one-sided alternative. I want to know if the true value p is bigger, greater than 0.6, and the lower bound being 0.615 or so lets me know that the value of p of 0.6 is not really plausible. I know that in theory, it's possible that if the true value of p was 60%, I could get a quirky set of data values where 70 out of 100 times I do see my event of interest occurring. How likely is that? Well, the p-value lets me know. The p-value of this test is about 0.025, less than 0.05, so I'm rejecting the null hypothesis in favor of the alternative. I do have good evidence that the probability of doubling my money is bigger than 60%, and that's what the confidence interval was saying. 0.6 isn't in that interval. I reject the null, go with the alternative here. And specifically that 0.025 is letting me know that had the true probability of me doubling my money was 60%, the value specified in the null hypothesis, there's only a 2.5% chance of observing 70 successes or more out of those 100 trials. Basically measuring a p-hat that's at least as far above that hypothesized value of p of 0.6 when I went and collected data. So the two end up getting into the same place. Once again, that p-value being a comment about the probability of observing your sample, or a sample that provides even more evidence for the alternative, if in reality that null hypothesis is true. And then finally, if we're comparing those two return rates of those two different colors, the orange and the orange-red, if we throw that into t.test, we can answer the question about the difference in return rates in two different ways, with the confidence interval or with the p-value. So in this case, the way that I was setting it up is that I was curious to know if the return rate of orange was less than the return rate of the color orange-red. So what I end up finding is I found that the difference in averages was 0.21 versus 0.22, a very small difference in average. If I get my 95% confidence interval out, what I find is that the confidence interval actually contains 0. So 0 is a plausible value for the true difference in return rates between these two colors. I continue to favor the null hypothesis since 0 is a plausible value. If I look at the p-value of the test, I get a p-value that's above 5%. So once again, a p-value bigger than 5% lets me know that I continue to favor the null hypothesis, the claim in the null hypothesis that those two return rates are equal. Not enough evidence, not enough of a difference here for me to go with the alternative. Now, when we are conducting a hypothesis test that compares, say, probabilities or averages between two different groups, that null hypothesis is always going to be that the probabilities are the same, the averages are the same. The alternative is that they're different in some way that we find interesting. But when we reject the null hypothesis, when we find that 0 is not a plausible value for the true difference, we say that the difference in the two groups is statistically significant. And that's when our ears perk up in analytics. We're always looking for statistically significant differences because that tends to give us actionable insight, like, hey, we need to go look at this orange-red color, see what's wrong with it. So one big caution that you want to keep in mind when your hypothesis test leads you to reject the null hypothesis and you find that the differences in two groups is statistically significant is whether or not that difference is big enough for you to actually care about. In business analytics, we're all about discovering actionable insight, and having statistically significant differences is a prerequisite for having actionable insight, but it might be the case that those differences are too small, that they don't really suggest anything interesting for us. So, for example, imagine we're comparing the donation rates between two different groups of people. People that live in urban areas and people that live in suburban areas. Imagine we have a sample of 100,000 people that live in each of these areas here. Now, it might turn out that our data says that people in urban areas donate at a slightly higher rate. So if we go and run prop.test on our data, we might find that the probability that someone that lives in an urban area donating is 50.3%, whereas the probability of someone living in a suburban area a little bit lower at 49.7%. Prop.test or binom.test lets us know that the difference is statistically significant because that p-value is less than 1%, less than 0.05, so we reject the null hypothesis that they're equal. We favor the alternative that they're different in somehow. But notice that the confidence interval, this is why we like confidence intervals so much, lets us know that the difference in these probabilities is really quite small. So yes, the difference is statistically significant, but it's a pretty small difference. We're 95% confident that it's somewhere between about 1% down to 0.1% or 0.2% here. Is that big enough to really mold our donation strategy for getting more donors into like suburban versus urban strategies? Well, probably not. That's not really that big of a difference to guide strategy. And that's what we always want to keep in mind. In business analytics, we're always looking for that actionable insight. When we find statistically significant differences, that gets us excited. That suggests that, hey, maybe we can do something with these results. Always make sure that you're following up statistical significance with the question of, well, how big of a difference are we really seeing? Is it big enough to have any sort of practical importance to help us guide our decisions here? Just because the difference is statistically significant doesn't mean we can act on it, that it's big enough to be interesting here. And that's another reason why we like confidence intervals, because the confidence intervals let us know just how big that difference might be. Once we've concluded our hypothesis test, we'll either continue to favor the statement made in the null hypothesis or we'll favor the statement made in the alternative hypothesis. And just like everything else in all walks of life, there's going to be a chance that the hypothesis test makes a mistake. We may end up favoring the correct statement, or we may make a mistake and end up favoring a wrong statement. So when the hypothesis test has concluded, one of four things will have happened. Number one, we'll have either correctly retained the null hypothesis, meaning that we continue to favor the null hypothesis, and that's a correct statement about reality. Number two, we might reject the null hypothesis. We might end up favoring the statement in the alternative hypothesis, and that's the one that actually describes reality. Or we might make one of two errors. We might reject the null hypothesis, end up favoring the statement made in the alternative hypothesis, but in reality, the statement in the null hypothesis was true. Or the other type of error, the other way around, we might end up retaining the null hypothesis and continuing to favor the statement made by it, but in reality, it's the statement in the alternative that actually describes the world. And if we think about it, if we really think critically about what a hypothesis test is doing, we kind of realize that actually at the end of every hypothesis test, we're probably always going to be making a mistake if we retain the null hypothesis. I'm going to be relatively bold and say that almost every single time you want to run a hypothesis test, the null hypothesis is going to be false. And I think this is one of the really big problems with hypothesis testing. I feel like the null hypothesis is always going to be wrong. In business analytics, we're usually looking at differences in probabilities or averages between groups. And is it really realistic to think that both groups are going to have exactly the same probability or exactly the same average? I don't really think so. I feel like they're going to differ, maybe in a very small, non-substantial, non-interesting way, but there is still going to be a difference. And likewise, if we have a penny in front of us, do we really think that that penny is perfectly fair? That there's exactly a 50% chance of that coin coming up heads versus tails? Well, probably not. There's some sort of defect in manufacturing. There might be some dirt or dust on the coin that gives it a very slight bias to coming up heads or tails. So if our null hypothesis is saying that the probability is 50% that it's a fair coin, I kind of feel like that's just a wrong statement to make. Going into probabilistic modeling, that all the models that we propose are wrong, some are just going to be useful. So, in my opinion, this is another huge problem of hypothesis testing, is that we kind of go into it a priori knowing that the claim made in the null hypothesis is incorrect. And so hypothesis testing doesn't really get us to where we really want to end up. We'd like to test the following. We'd like our null hypothesis to be that the difference in maybe the averages between two groups A and B is so small that it doesn't really carry any sort of practical consequence to us. With the alternative, the claim that requires a bit of evidence that the difference in averages between groups A and group B is large enough to be of considerable interest, to actually give us some sort of actionable insight. And really, that's the problem with hypothesis testing. It's not really answering the questions that we have. Confidence intervals are a little bit better of a method, I think, coming up with a range of plausible values for the difference in the averages between two different groups so that we can gauge for ourselves what size of a difference we're actually talking about and if we really care about that size of a difference. But because we are kind of stuck with the hypothesis testing framework for some questions, like is there a hot hand, is there clustering at all in this collection of data points, we should be relatively comfortable talking about the probabilities of making both of those two different types of errors, and also making the right decision, favoring the null when it's true and favoring the alternative when it's true. So let's talk about the two types of errors we might make when a hypothesis test is conducted. So the type 1 error occurs when we reject the null hypothesis when in reality it's the correct statement about the world. So in other words, we end up favoring the claim made by the alternative, but in reality the claim made in the null hypothesis is correct. Now, the good news is that we have complete control over the probability of making this type of error. In fact, that threshold where we were checking to see the p-value if we continue to favor the null or go with the alternative, that threshold of 0.05 actually is going to be the probability of making a type 1 error. In general, in hypothesis testing, we symbolize that threshold, that probability of making a type 1 error by the Greek letter alpha. And why is it that we have complete control over that? Well, remember what that p-value was trying to hit at. It was basically saying that when the null hypothesis is true, there's a 5% chance of observing your value of the test statistic, your data that you just collected, or even more evidence for the alternative. So even when that null hypothesis is true, we're going to get kind of quirky oddball samples. We're rejecting the null hypothesis and favoring the alternative when that p-value is less than 0.05. And that's going to happen for 5% of random samples when the null hypothesis is indeed true. So this 5% standard is just so universal that you don't really want to mess with that. You definitely don't want to be disingenuous and choose what that threshold for the p-value needs to be for you to reject the null hypothesis and favor the alternative after you've collected your data so that you kind of tweak your conclusion based on what you want to discover. You want to keep to that 5% threshold when you're looking at those p-values, and that's tied into the type 1 error rate. So type 1 error of 5% is tied into that confidence of 95%. We know that if the null hypothesis were true, well, our 95% confidence interval is going to miss the true value of the parameter it's trying to estimate 5% of the time. It'll capture it 95% of the time. So it's going to make that error 5% of the time as well. It's going to miss the true value of the parameter we're trying to estimate. So we'll stick with that 5% value that's just so standard universally in business analytics and in science. There's no reason to mess with that. And so we'll always know that when we conduct a hypothesis test, there's going to be a 5% chance of us favoring the alternative hypothesis when in reality the statement made by the null was the correct description of the universe. Now, the other type of error, the type 2 error, when we actually end up continuing to favor the null hypothesis when in reality the claim made by the alternative is true, the claim made by the null hypothesis is false, this one's a bit more difficult to calculate the probability of because it depends on actually a few things. Number one, it's going to depend on the effect size, basically how wrong the null hypothesis is. If the value that's proposed by the null hypothesis is just a little itty bit wrong, let's say the probability of coming up with the heads is 50.005%, most likely we're going to end up retaining the null hypothesis, continuing to favor the notion that it's a fair coin, when in reality it's just basically just a little bit unfair here. So it's going to depend on just how wrong that null hypothesis is. It's probably going to be pretty easy to detect if the probability of coming up heads is like 80% or 90%. And it's also going to depend on the sample size. So let's actually see a demonstration of this so we get a better feel over what the probabilities of these two different types of errors are. Normally, we don't talk about that probability. Instead, we talk about the power of the test instead. The power is the probability of correctly rejecting the null hypothesis. So correctly favoring the statement made by the alternative when the null hypothesis is wrong. And since we're going into it pretty much knowing that the null hypothesis is always going to be wrong, how do we actually, how often do we find that that is the case? How often do we correctly identify the null is wrong? So let's take an example, fair coin example. So our null hypothesis is that the probability of coming up heads is 50%. It's a fair coin. The alternative hypothesis is that it's unfair. The probability of heads is not 50%. So let's imagine in reality that the effect size is 0.05. So in other words, the actual probability of coming up heads is 55%. There's a 5 percentage point difference between what's proposed in the null hypothesis and what's going on in reality. And let's see just how often our hypothesis test actually identifies this, that we should be rejecting the null hypothesis and favoring the alternative, that it's not 50%. So I can flip a coin, let's say 160 different times, where I have the probability of coming up heads be 55%, and maybe I find that 83 out of these 160 flips come up heads. Well, I can shoot this into binom.test to get a 95% confidence interval for the true probability of it coming up heads. And in this case, I would say I'm 95% confident that the true probability is between about 44% and 60%. So notice that 50%, the value that's claimed in the null hypothesis, that's smack dab right in the middle of the confidence interval. So we end up continuing to favor the claim made by the null. The value proposed by the null is right inside that confidence interval. So we continue favoring the null hypothesis. And we made an error. By design, we know that the true probability of coming up heads is 55% in this case. And so we made this type 2 error. We end up retaining the null hypothesis when we should have rejected it. But that's a fact of life. We're not always going to make the right decision. So we might actually be interested in looking at a Monte Carlo simulation that estimates the probability of making this type of error. What is the probability we'll make a type 2 error? And also, what's the power of this test? What's the probability that we'll correctly reject the null hypothesis, since in reality, the probability of it coming up heads is 55%, but the null hypothesis is claiming that it's 50%. So let's run a Monte Carlo simulation where we basically flip a coin 160 times. We count up the number of heads that result, and we shoot that into binom.test, extract out the confidence interval, and look to see if 50% is somewhere inside the lower and upper bound. If so, we end up retaining the null hypothesis, continuing to favor it, and so let's see how often this occurs. So after running a total of 10,000 different trials, what we find is that the type 2 error rate for this specific instance is right at about 76%. 76% of these random samples are yielding confidence intervals that contain 0.5, making us continue to favor the null hypothesis, since that's the value that the null hypothesis is specifying. And so we're getting it wrong. We know by design the true probability of it coming up heads is 55%. That's a pretty high chance of making an error. The flip side, the power of the test in this specific example, the probability of us correctly rejecting the null and favoring the claim made by the alternative, that the probability is not 50%, is kind of a scant 24% here. Not very large. But like I was saying, the probability of this type of error actually depends on just how wrong the null hypothesis was, and really what the sample size is as well. Let's kind of take a more extreme example where we have a lot more data. Let's say we have, data on 1,600 coin flips. You know, the more data the better we've estimated what the true probability is of coming up heads. So we should have a higher power with this sort of test. We should have a lower type 2 error rate because we've been able to nail down the probability of coming up heads a little bit more accurately. Well, running the same Monte Carlo simulation, what we find is that our type 2 error rate is now only about 2%. Only about 2% of the time, we end up with a random sample whose 95% confidence interval happens to still contain 0.5, making it look like it's a plausible value and making us continue to favor the claim in the null hypothesis. The power of the test is right at about 98%. There's a 98% chance that we're going to be able to tell from this data that we've collected that the null hypothesis is wrong. Now, as I was saying, this also depends on the effect size, just how wrong the claim made by the null hypothesis really is. And so we can look at an animation to see how the power of the test depends on this effect size. So as we look at probability of coming up heads being farther and farther away from 50%, what we find is that the power of the test continues to increase. The probability that our hypothesis test correctly rejects the null hypothesis in that case continues to get bigger and bigger. And that makes sense. The null hypothesis that's more wrong should be easier to detect, and we find that that's the case. If the claim made by the null hypothesis is just barely wrong, well, there's not a very good chance the hypothesis test or confidence interval is going to be able to detect that. And so that's just one of the drawbacks that we have with hypothesis testing. If that claim made by the null hypothesis is just barely wrong, it's going to be really difficult for the hypothesis test to come up with the correct conclusion. It's going to be really hard for that hypothesis test to reject the null hypothesis. And so, likewise, we can see how the power curve changes depending on the amount of data that we've collected. As we collect more and more data, as we add more and more flips to our random sample, we can see the shape of the power curve changes, basically allowing us to have a higher chance of correctly rejecting the null hypothesis for values of the true probability of coming up heads that are closer and closer to that 50% level, that value that's claimed in the null hypothesis. So unfortunately, it's just a sad fact of life that we're going to have to deal with errors in hypothesis testing. We have two different types of errors. That type 1 error, where we reject the null hypothesis and favor the claim made by the alternative, even though the claim in the null hypothesis is the correct description of reality. The good news is that we know what that probability of making that error is going to be. We denote it by alpha. We take it to be 5%, and that we just kind of stick with. That's the standard. The other type of error, the type 2 error, is a little bit more insidious. That type 2 error means that we've retained an incorrect null hypothesis. We've continued to favor the claim in the null hypothesis when in reality, the claim made by the alternative is true. And that's probably where we're going to be most of the time in real life. I don't really think the null hypothesis is ever really true. And so the probability of this type 2 error, or really more interestingly, I think the power of the test, the probability of us correctly identifying that the null hypothesis is wrong, it's going to depend on just how wrong that null hypothesis is, the effect size. The bigger the effect size, the more wrong the hypothesis is stated in the null, the easier it is going to be to reject it. And so the larger the effect size, the higher the power of the test. And then also the more data that we have, the more power of the test as well. And the you want to make sure that the lights are timed optimally. And so maybe a month ago you measured optimally. but traffic patterns change over time. Maybe a month ago you set up the lights to have perfect timings, and you'd like to know how traffic's pattern less than a one. So what we'll do is we'll start out by favoring the null hypothesis, and we'll continue to do so until the evidence suggests otherwise. Kind of like in that was not cool.